Yesterday, the last topic that we didn't cover was differential evolution. This is the last metaheuristic we will cover in this course. In here, this is a very recent picture from last year. This is Kenneth Price, and this is Rainer Storm. These are the guys who invented differential evolution. This picture was taken at the banquet of CEC 2017 last year in Spain, when they received the Evolutionary Computation Pioneer Award from the Computational Intelligence Society. So this is a relatively recent heuristic in the sense that it was created in 1995. The story of this heuristic is also very interesting. The inventor is really this guy, Kenneth Price. He was a student of Rainer Storm at University of California at Berkeley. And Rainer Storm challenged his students to solve a very famous nonlinear optimization problem, the Chebyshev polynomial feeding problem. And he said he would give an A to a student who could produce an algorithm that was better than the traditional mathematical programming techniques, and that was of his own creation. So Kenneth Price came up with the idea of using these vector differences for perturbing a vector population, show the algorithm to Ken Price, to Rainer Storm. He made some suggestions, and then they released this as a technical report from Berkeley in '95. And 1997, they published this journal, this work in the Journal of Global Optimization. So it's a very interesting algorithm. It has several similarities with evolutionary algorithms. However, one important difference is that differential evolution, in its original definition, only operates with real numbers. So it doesn't allow binary, integers, any other encoding, only real numbers. Doesn't require also a probability density function for adapting parameters. This is something that evolution strategies use. And it performs mutation based on the distribution of solutions in the current population. So it's a very simple idea. You will see the pseudocode. The code is available. There is a website devoted to differential evolution where you can download the code in C. It's only 1.5 pages. It's very short. After the paper from '97, they created this nomenclature to designate the different versions of differential evolution. So they use DE, which stands for differential evolution, then slash. In this case, RAN means that the individuals selected to compute mutation are randomly chosen. 1 means we get one pair of solutions, and being means that we use binomial recombination. There are several other versions of differential evolution, but this version, RAN1 being, is the one that is normally used. Most people use this one. So this is the algorithm. It's very simple. So all this part is standard. We create a population. It's initially generated randomly. And the interesting part is this. We select 3 solutions randomly, which are meant to be different. And an index is generated randomly between 1 and the number of dimensions of the problem. And this is the main operator of differential evolution. So you see, one individual is added to the difference of 2 other individuals multiplied by f. This f, at the beginning, most people didn't know what it was. However, if you are familiar with classical optimization techniques, you can probably realize that doing something like this is very similar to having a gradient here, lambda, and an initial point. In mathematical programming, unidirectional search operates this way. It doesn't really matter if you do it x1 minus x2 or x2 minus x1. How you do the difference is not that important, because the index it only corresponds to random solutions. So they claim that with this, they are estimating the gradient in a region, not in a point. However, if you see, they are only using decision variable values. They are not using objective function values. So it's very intriguing. However, the algorithm works very nicely. It's a very powerful optimizer. Some people consider this to be a mathematical programming technique, although it has some stochastic components. So, okay, in that pseudocode, run in is a function that returns an integer between these two limits, min and max. Run 0, 1 is a function that returns a real number between 0 and 1. And in both cases, these functions are based on a uniform probability distribution. And from the other parameters, the only one that is, there are two that are important. CR, which controls the influence of a father in the generation of the offspring, and F, that scales the influence of the difference. So CR, if you have high values, that means less influence from the father. And F, basically, as I said before, it was unknown at the beginning what value should be given to F. So some people gave a value of 1, which is no effect, or something like 0.5. But over the years, people discovered that this was an important parameter. And if you modify this parameter, the behavior of the algorithm will be modified. So if we increase the population size of differential evolution, then, or we increase the number of pairs of solutions to compute the mutation values, this is meant to increase diversity. So this is sort of the source of diversity in the algorithm. However, if we do this, at the same time, the probability of finding the correct search direction also decreases. So this is sort of a dilemma. If we want to have a better diversity in differential evolution, it's recommended to use more solutions. But if you do that, then perhaps differential evolution will no longer be a powerful optimizer. So normally people tend to use differential evolution with reasonably low population sizes, about perhaps 100 or 200, but not with 1,000 or 5,000 individuals, because if you increase too much population size, then you are decreasing the effectiveness of the algorithm. So this is an interesting issue. Some people have looked into this. Differential evolution has been studied from all different perspectives. So we're going to see very quickly the 8 different differential evolution variants that are proposed in the original paper from Price and Stone in 1997. So we have first 4 variants in which the recombination operator is discrete, and it always uses 2 individuals, the original father and the mutation vector of differential evolution. So in here, the change is in step 11. All the steps with the arrows are those steps that change in the different versions of differential evolution. There are 2 types of discrete recombination, binomial and exponential. By discrete, I don't mean that this operates with integers. This is just the name of the recombination. It always operates with real numbers. So the main difference between binomial and exponential recombination is that if we use binomial recombination, each decision variable of the offspring is taken each time from one of the 2 parents. This is based on this parameter CR. If we use exponential recombination, then each decision variable of the offspring is taken from the first father until a certain threshold or value exceeds the value of CR. And from that point on, all the values of the decision variables of the offspring are taken from the second parent. So you can see that in here, you are taking a consecutive number of values from the first father, and then CR will tell me in which moment should I stop and then go for the other. Whereas in the first case, the idea is that based on CR, each time I choose one, I can choose it from the first or the second parent. So the first is more like what we call uniform recombination in genetic algorithms. in which if, for example, CR is 50%, then half of the decision variables will come from one father and the other half from the other. It's just they are not going to be distributed in a uniform way. It depends on the randomness of the distribution. So these 4 variants are called rand 1 bin, rand 1x, base 1 bin, and base 1x. So the rand variants select the individuals to compute mutation in a random way. And when we use best, like in these two, that means that the best solution in the population is combined with the random ones. Remember, there are three parents, right? We have, this is one, and these are the other 2 parents. So in the first, the 3 are random. In the other, this is the best, and the other 2 are random. So that's really the difference. There are 2 other variants in which arithmetic recombination is used. So this one, unlike discrete recombination, is invariant to rotation. So some people like that, but this version is not very common. These 2 variants are called current to rand 1 and current to base 1. And the only difference is that in the first, current to rand 1, we select the individuals for mutation in a random way. And the second, again, we take the best solution plus 2 randomly generated solutions. There is another one, rand 2 dir, which incorporates information from the objective function into the mutation and recombination operator. So the idea here is to speed up convergence. We want to converge faster by using information obtained from the search process. This is a non-standard version. This guy, Feokstitskop, he published a book on differential evolution some years ago in which he elaborates on the reasons for doing this. And finally, there is another variant that uses a combined discrete arithmetic recombination. It's current to rand 1 bin. This is also not very common. Okay, so now we go to the multi-objective extensions. Apparently, this paper from '99 is the first attempt to extend differential evolution to multi-objective optimization. In this case, the authors adopt an external archive, which they call Pareto optimal set, to store the non-dominant solutions, which is very interesting because this was '99 and external archives were not very common at that time. He also uses fitness sharing, which is very uncommon in differential evolution. And the selection mechanism of differential evolution is modified to force it to produce non-dominant solutions which lie at a certain minimum distance from those that had been generated before. So this is more like a local search mechanism. It's a very interesting paper. Berge also in '99 reported a multi-objective evolutionary algorithm based on differential evolution almost at the same time as Chang. And this was called Pareto differential evolution, which is kind of the obvious name, the obvious acronym. However, the paper doesn't provide much detail on how this algorithm works. They only say that it generates non-dominant solutions and that is implemented as a general purpose solver, which is embedded in Excel. It's kind of a paper that is totally unclear about what they do. And PDE is really designed to be used for multi-criteria decision maker. This is the topic of the next lecture. As we will see, decision making refers to selecting solutions from the non-dominated set. Hussein Abbas, and this is probably the version that is best known of multi-objective differential evolution, he proposed the Pareto Frontier differential evolution, whose acronym is the same. It's also PDE. This was presented first at a conference in 2001 at CEC, and then it was published in a journal. In this case, the population is initialized using a Gaussian distribution with a mean 0.5 and a standard deviation 0.15, and only non-dominant solutions are retained to be recombined, so this is a mating restriction. If the number of non-dominant solutions exceeds a certain threshold, in this case it's 50 solutions, then they use a distance metric to remove parents which are too close from each other. So this is similar to fitness sharing or niching. As in traditional differential evolution, they use 3 parents to generate 1 offspring, and the offspring is placed in the population only if it dominates the first selected parent. Otherwise, selection is repeated. Madhavan proposed the Perito Base differential evolution, very similar name, and this is basically a version of NSGA2 in which he replaces the genetic algorithm by differential evolution. So there is nothing really new about this. In this case, one difference is they use some test problems that are more common, like the ZDT, but the algorithm is not able to converge in multifrontal problems, for example, ZDT4. Bing Xu, this guy, he did his PhD thesis in the US on MODE, this multi-objective differential evolution, which is a variant of differential evolution in which only the best individuals are used to create an offspring. This is similar to Hussein Abba's idea. It uses Pareto Base selection and crowding, so it's similar to NSGA2, and non-dominant solutions are stored in an external archive. Parsopoulos, the same guy who did BEPSO, he also did a differential evolution version of BEPSO. So this is Vega, but using differential evolution. He uses, in this case, M subpopulations within a ring topology. Each subpopulation is evaluated using the objective functions of the problem, and there is an exchange of information among them through the migration of the best individuals. There are many other versions of differential evolution. For example, Xiaodong Li proposed also another version of NSGA2 based on differential evolution called NSDE, or non-dominant sorting differential evolution, in which the search engine is a DE current to run one differential evolution algorithm. There was another version of NSDE that was presented at Gecko 2006 that incorporates directional information regarding convergence and speed, and they modified the algorithm so that the offspring are generated in the direction of the previously generated solutions having a better rank. Okay, there we go again. Okay, let's see if the thing crashes, because normally it crashes afterwards. Yeah, it will crash, of course. Okay, and in this case, for the density estimator, they modified the algorithm so that it favors the selection of individuals from different regions of decision variable space. It's similar to crowding. It's a similar operator. Saku Kukkonen in Finland, he developed a revised version of an algorithm that was developed by his advisor, by Jouni Lampinen, called Generalized Differential Evolution. This is actually a very interesting algorithm because the algorithm is able to solve single objective and multi-objective problems without any changes, and also unconstrained and constrained problems. So he extended the selection operator of differential evolution to handle constrained multi-objective problems. The original one is only for single objective. And the idea is that the trial vector must dominate some members of the old population used as a reference, either in terms of constraints or in terms of objective function values. If there is a tie, then the vector that resides in the least dense region of the search space is selected. So there were other versions. The last version was this, GDE3, presented at CEC 2005. And this one considers Pareto dominance when comparing feasible solutions and weak dominance when comparing infeasible solutions. So it does something similar to NSGA2 of trying to obtain a complete order, but giving priority to Pareto optimality, that this has to be strict, and then when there are ties, he breaks the ties using constraints. So it's really a very simple idea. Another well-known algorithm is this one, DEMO, proposed by Thea Robic in 2005,
differential evolution for multi-objective optimization, which is also another version of NSGA2 using differential evolution. It maintains one population and it's extended when newly created candidates take part immediately in the creation of the subsequent candidates. So they show that contributes to accelerate convergence. We also developed one many years ago with Luis, who was first my master's student and then my PhD student. Again, the guy had no creativity for names, so he didn't know what name to use, so he put MyDE, my differential evolution, because he didn't know what name to give it. It uses epsilon dominance and has nothing really that novel, but it worked. Some years later, with Alfredo, is a Spanish guy that was our collaborator for several years, he hybridized this algorithm with ROP sets to produce Demors. Demors is a very interesting algorithm because it converges very quickly to a few solutions, and then ROP sets are used as a local search algorithm to generate more solutions in the vicinity of these few solutions, so we can approximate Pareto fronts of problems having up to 30 decision variables, performing only perhaps 3,000, 4,000 objective function evaluations instead of 20,000, 30,000 that most algorithms require. There have been some others. For example, of course, there is a version of MoIA-D based on differential evolution. It's called MoD. And there was a version that deals with variable linkages that was proposed in the year 2006. And it's just an out-of-the-box version of of MoIA-D using differential evolution. Applications, there are several. As I said, it's possible, and there are versions of differential evolution for binary encoding and for integer encoding. But as far as I know, the best performance of differential evolution you will have in continuous optimization problems, when all the decision variables are real numbers. You can find here, for example, some people have used this for flow shove scheduling, but I believe it's not as good as in continuous optimization. To give you an idea, back in the year 2003, 2004, when I was working on constraint handling, at that time we were testing evolution strategies and genetic algorithms with real numbers encoding for solving constraint optimization problems. And the evolution strategy was clearly better than the genetic algorithm in continuous optimization, but still, when we perform, for example, 30 runs in some very difficult constraint optimization problems, the evolution strategy was able to converge successfully, perhaps in 15, 20 of the 30 runs, and in the others, it produced a good solution, but not the best solution known or the optimal in some benchmark we were using at that time. So one of my students who was working on that area, he decided to implement differential evolution, keeping the same constraint handling technique we had before. When we implemented differential evolution, in the same problems, we will perform 1,000 independent executions, and in the 1,000 executions, differential evolution could hit the same solution, which was the optimum, so the standard deviation was 0. It was really amazing. It was like using a deterministic algorithm. So it's very powerful. The only weakness of differential evolution is scalability. It's not suitable if you have too many decision variables. More than 100 is, it will work, but the performance will quickly degrade as you increase dimensionality. You want to know more? We have a survey published several years ago, and also in my book you can find some information about multi-objective optimization using differential evolution. Okay, so I don't know if you have any questions. With this, we finish the topic of multi-objective meta-heuristics.
Can we generalize that the number of iterations for differential evolution will be less for a particular test function as compared to other strategies?
You mean the number of iterations that you require to converge? But in multi-objective or single objective? Multi-objective. In multi-objective differential evolution is not as good as it is in single objective.
It's good, but no, I will not say it is the best. It's about the same as using genetic algorithm. In single objective, you can reduce the number of iterations.
But problem which I see, I'm not sure whether it's right or not, but mutation operator is exhaustively used in the differential evaluation.
Sure, it's a combined operator. It has crossover and mutation. But
crossover usually takes after the mutation. Isn't it something?
No, it's the opposite. You first do crossover and then you do mutation. But in this one, they do both. So it's a very weird thing. The mutation is sort of a fuzzy concept in differential evolution because the operator is supposed to combine them. However, there is one step in which you can modify a single variable. So that works like a mutation operator. But it's very good. It's a very good algorithm. The problem in multi-objective is that since you are not aiming to get a single solution, then it will converge very quickly to the vicinity of the two Pareto. But then spreading the solutions, it takes a lot of computational effort. So my guess is it would be better, for example, if you use something like MoIAD with differential evolution, because MoIAD is doing single objective optimization. So in that case, I would expect a better behavior. But any Perito Base algorithm is not that. You lose most of the power of the algorithm. You lose most of it. Any other questions? Before we move to, we're going to talk now about multi-criteria decision making, which is the last topic. And then I have a very short talk about some of the challenges in the area. Okay. If you have no questions, then we will move to multi-criteria decision. This is also this is a performance indicator. It's sort of a not very nice topic, but we have to swallow this thing. So something that is really very important in real-world applications and that most people in this area, in evolution and multi-objective optimization, tend to disregard is what we call the decision-making process or the incorporation of users' preferences. It is normally the case that in real-world problems, the user is not interested in having 100, 300 non-dominant solutions. They only want to have few so that he can choose one from this small set. And at the end of the day, if you are designing something, a device, the wing of an airplane, a refrigerator, whatever you are optimizing, if you are going to physically implement the solution, you cannot afford implementing 100 different solutions, right? You can perhaps afford 2 or 3, but no more than that. So the question is, how can I bias the search so that the evolutionary algorithm only produces solutions in the region that I'm interested on? So that's really the main issue. So that's what this topic is about, incorporation of users' preferences. So from the operations research perspective, and I'm now stepping into that area, as Professor Figueira's area, there are two main lines of thought regarding multi-criteria decision making. The so-called French school, which is based on a concept called outranking, which probably Jose talked to you about this. And then we have the American school, which uses a concept called multi-attribute utility theory, which was, of course, proposed in the US. So we will see very quickly the difference between the two, and then we will see some examples of how this is used in evolutionary algorithms. So this outranking relation is constructed from several pairwise comparisons of the objects that we are studying. The objects are basically the alternatives that we provide to the decision maker. So each object can be seen as a non-dominant solution. So we ask the decision maker, please compare this solution to this other solution. So these are the two objects. And the decision maker has to provide a preference, saying, okay, I prefer solution A over solution B. No explanation is required, only selecting. You have to select. So the alternatives are if there exists preference, indifference, or incomparability. So there are three possibilities. You can say, okay, I prefer A over B, or you can say I am indifferent, which means you can take any of the two, or they are incomparable, which will mean they are both equally good or equally bad. Right? It's just I cannot compare. And there are some indicators to define this. The main disadvantage, it has two disadvantages. One is it can be very expensive, computationally speaking, if you have many alternatives, many solutions. And also, another disadvantage that is more important is that the pairwise comparisons that we perform allow intransitivity. That means that the decision maker can contradict himself and still the solution will be valid. We will see that in multi-attribute utility theory, no contradictions are allowed, no intransitivities are allowed, so the total decision-making process won't have any contradictions. So this mathematically is a problem, of course. But at the same time is an advantage in the sense that it gives more flexibility to allow contradictions because humans tend to contradict themselves. Right? So the other one, the American school, is based on the formulation of an overall utility function, and the underlying assumption here is that such a utility function is available or can be obtained through an interactive process. That means we are asking the decision maker to provide information to construct this utility function. Now, when the utility function is not available, then the task will be to identify a set of non-dominant solutions, and we have to try to decide directly on that set of solutions. In this case, we have weak preference, which is modeled mathematically as weak dominance, and this expresses a lack of conviction. So I can say I prefer A over B, but I'm not completely sure of this. I'm hesitating of this decision. Indifference means that the two vectors are equivalent, and therefore it doesn't really matter which of the two I select. Indifference is not the same as incomparability in outranking methods, because in outranking methods, incomparability refers to vectors with strong opposite merits. So it has sort of an abstract difference. So as I mentioned before, in multi-attribute utility theory, intransitivities are a problem. They are not allowed in the preferences. And this may happen when dealing with incomparable objects, particularly in the outranking approach. There are also a few other issues. For example, it's important to distinguish between global and local approaches, because we can have a global utility function as opposed to a local utility function. The difference is the local will be built based on comparing a small set of objects, not all the solutions, and the global will be obtained from comparing everybody against everybody else. So normally it's assumed we have a global approach, and this overall utility function that we construct expresses the global preferences. But in practice, this is not always the case. Sometimes we are unable to produce this global, and we just assume it's global, but it's really local. There are other issues that are more subtle regarding utility functions. For example, some people have argued that utility functions do not really reflect the decision maker's inner intensity of preferences, but only a model of the behavior of the decision maker. This is an important distinction, because behavior should really be consistent. But in practice, humans are complicated, we are complicated, and sometimes our behavior is inconsistent. I don't know if you have fill out these surveys. From time to time you get in the internet some surveys from companies for a product, or you bought a book, or you went to the movies, and they ask you something about some topic. If you are filling out a survey, a questionnaire, and it has few questions, let's say 10 questions, and you are in a good mood, you are probably going to finish in 5 minutes. But if you get a survey with 100 questions, at the beginning perhaps you are okay. You say, okay, I will do it. Now some surveys tell you before you start, this thing will require 25 minutes of your time. So they are warning you, right? But, computer scientists, we don't read instructions. You just go to the survey and don't care. But of course, after 10 minutes, you are complaining and say, what the hell is this? You know, I have been answering questions and questions. Last night, I did one of these surveys, and halfway done, I wanted to quit because I felt that some questions I was asked at least 5, 6 times, the same question, because I think this survey identified contradictions. So when it detected a contradiction, they will throw the same question again, just to make more consistent the responses. Because they realized that after a certain amount of time that you have been responding these questionnaires, you are fed up with the thing. You don't want to do it anymore. So you randomly respond whatever you want. So that the same thing happens here. If you are shown solutions several times during a long time, at some point, you are going to be completely tired and you won't care anymore what solution is selected. So your answers are going to contradict preferences that you expressed before. The thing is, with this model, with multi-attribute utility theory, this is not allowed. So the system either will tell you that you are contradicting yourself or will crash because you gave a contradiction. In outranking, contradictions are allowed. You can do it. But of course, the outcome will be different. Outranking behaves more like a genetic algorithm. Each time you run the thing, depending on if you have contradictions or not, the outcome will be different, providing the exact same information. So some people don't like it because of that. So the main criticism in this case is the inability of multi-attribute utility theory to handle intransitivities. However, they give arguments of why intransitivities should not be allowed. For example, they say it's only concerned with the behavior, and the behavior has to be transitive. Transitive is often a close approximation to reality, and the interest of the method is limited to normative or idealized behavior, so not the real behavior of humans. And transitive relations are, of course, far more mathematically tractable than intransitive ones, which is the real reason why intransitivities are not allowed. If you allow intransitivities, then the mathematical model is no longer possible. So you have to deal with graphs and sort of partial models, but not a full model of the behavior of the decision maker. However, it is true that in real life, humans tend to contradict themselves, not necessarily in an unconscious way. Sometimes we change our opinion. At the beginning, if we have little information about the decision that we are going to make, we may decide for something completely different than when we have much more information about this. So this may, of course, happen in real life. So based on these two schools of thought on multi-criteria decision making, there are 3 types of operational attitude of the decision maker. We can exclude incomparability, and then by excluding that, not allowing the user to say these 2 solutions are incomparable, then we can completely express preferences using a unique criteria. And in this case, we can use an aggregating function, so everything is very easy if the user is not allowed to say these 2 solutions are incomparable. Second option is we accept that the user will say some solutions are incomparable, and we use, in that case, outranking to model the preferences. And what outranking does is, if we have comparisons in which no incomparability appears, then we use a utility function. And we only use outranking when there is incomparability. It's sort of a mixed approach. And the third is to use an interactive process so that the different compromises are based on local preferences, and these take us somehow to building a global model of preferences from the user. This is normally the approach people in operations research like the most, because interactive approaches are normally very, very nice. The only problem here is the user will be asked questions several times during the search process. So you need to be in a mood as a user to be able to respond to all these questions. And the process will stop, as we saw before, when it's no longer necessary to ask because it's clear we already have a solution has been chosen, or it's impossible to continue because there are no more choices to make. Okay. We already saw before there are 3 stages at which we can obtain preference information. It can be before performing the search, during the search, and after the search. As I said before, operations research people prefer interactive approaches. In evolutionary algorithms, we normally assume a posteriori approaches. That means that the decision-making process will take place after the search. The reason is that we always aim to generate as many solutions as we can, assuming no preference from the user, and we assume the user will be able to elucidate from this large set of solutions which one he or she wants. Okay, so there is a lot of work in operations research regarding prior articulation of preferences, these a priori techniques. They are very popular because this is the easiest way of doing it. If we can ask the user his or her preferences before doing the search, then if the user can really express these preferences, it's very, very simple. It is difficult, of course, to find a global preference function based on this information, unless the user is already familiar with the problem. But if you don't know the problem, it's very difficult to do this. So these a priori schemes are not very common in practice, although they are the easiest, because, as I said, in a real-world situation, you are solving a problem, a multi-objective problem for the first time. You don't have any idea of the possible trade-offs you will have. So you cannot decide ahead of time what do you prefer. If you don't have any idea what sort of compromise are you going to see. So people in operations research tend to favor interactive approaches. There are several reasons for that. For example, perception is influenced by the total set of elements in a situation and the environment in which the situation is embedded. This means it's not the same to make a decision without having any information that receiving information from the problem and asking you to make a decision. There is a big difference. This is like when you sign these agreements with Microsoft, all this software, that is a huge document, right? It's like 20 pages, or in the bank, it's 20 pages with very small font, and they just tell you, sign here. Most people, 99%, don't bother to read the thing. They just go and sign. I don't care. Then when you have a problem, you go complain and say, well, look at page 12, this paragraph that in the contract you signed, it says that I'm going to take all your money. But you signed that. You agree on this. So, of course, if you decide without having any information, the decision can be strongly biased in the wrong way. So perception is very important. Individual preference functions or value structures cannot be expressed analytically. So we assume, of course, the decision maker will be systematic in making his or her decisions, which is not always the case, but we assume this. But, of course, individual preference is very difficult to express with an equation. It's easier to ask the user to compare things. Value structures change over time, and preferences, of course, can also change over time. Once, perhaps at the beginning, you were aiming for a certain sort of compromise, and then once you start solving the problem, you realize there is another compromise possible, which is more interesting for you than the one you had in mind. So in that case, you will go for the new compromise. So this makes perfect sense. Aspirations or desires change as a result of learning and experience. Well, this doesn't always happen in life, but it's supposed to be the way the world works, right? As you have learned more and you have more experience, you are supposed to be able to make better decisions. This is not always true with humans, but it should be true. Right? At least if you made the same mistake, this time before making the decision, you knew this was going to be a bad decision. Right? But learning and experience should help somehow. The decision maker normally looks at trade-offs satisfying a certain set of criteria rather than optimizing all the objectives at a time. So this is also good because you are not seeing the solution of an optimization problem. What you are faced with is to decide. And we normally believe we are better to decide. That's also not always true, but some people actually like this. You know, like you are shown, for example, two different types of paintings, and you are asked which one do you like the most. And perhaps for many people, it's a lot easier to think in terms of that than to think in terms of the sort of painting that you are looking at. You know, one is perhaps a surrealistic painting, the other one is modern painting, but you don't know much about the different streams within art. You don't know much about art, so you don't want to be asked specifics about the type of painting. But you do have a taste. So you may say, I like this better than this other one. This is a lot easier. So it's the same here. Perhaps you don't know much about optimization because you are the user. You are not the guy who wrote the optimization algorithm. But for you, it's a lot easier to compare solutions that the system is providing you. You have no idea of how these solutions were obtained. You are only asked, please compare them and tell me which one do you prefer. And this most humans will be able to do. I don't know, of course, if the decision will be correct, because the thing here is there is no correct and incorrect. It's up to you as a user. Now, interactive approaches, of course, they are nice, but they also have some disadvantages. For example, the decision maker can be asked to rank a set of solutions, to estimate some weights, to adjust a set of aspiration levels. There are different ways in which you can be asked to do this task. These tasks, of course, are not trivial, and very often it will happen that the decision maker will give confusing or contradictory responses. There are, of course, algorithms that transform the information that is provided by the decision maker to a mathematical model, but in practice, simple trial and error procedures seem to work the best. Humans, we are not very complicated for this part. However, it's a lot more difficult to rank, for example, 10 solutions as opposed to comparing two solutions. Comparing two solutions is normally a lot easier. Tell me from these two which one is better. This is normally easier than if you are given 10 solutions and you are asked to rank the solutions in your order of preferences. Perhaps you can rank 3, 4 without much trouble, but the other 6 may be a problem. Okay, now when do we get the preference information? Well, the decision maker sometimes tends to be contradictory and inconsistent, and this, of course, is a bad thing because it's going to complicate a lot the decision-making process. And there are a lot of factors that could contribute to this inconsistent behavior. That's the reason why some people say it's better to use something that is not interactive. For example, the a posteriori approaches. In this case, the main difference and the main, well, some people see it as an advantage, is that the decision maker doesn't have to interact with the search engine. So you just run the optimization algorithm, the algorithm produces 50, 100, 200 solutions, and then you apply an algorithm or you ask the decision maker directly to analyze these solutions to choose which one do you prefer. So the problem here is normally the algorithms that are used to filter out solutions are very complex. These algorithms are very complicated, are also difficult for the decision maker. In many real-world problems, they are not applicable because the problem is just too difficult, and perhaps the solutions that were produced without any preferences by the time they are produced, they are not exactly what the user was expecting, and there is no way of going back because the optimization is over. And if you generate too many solutions, then this will make very difficult for the decision maker to select only one. So they do have disadvantages, but that's what we normally assume in the case of evolutionary algorithms. Of course, it's also possible to combine two or more of these approaches. For example, we could ask the decision maker some preliminary information if the decision maker knows something, and then do it interactive. So this will be a priori and interactive. At the beginning, give me some preferences. Doesn't really matter which preferences you express, because during the search, you are allowed to modify your preference. So this could be, as I say, in this area, we normally disregard the importance of incorporating preferences, and it's actually an area in which there isn't much work done. Most of the work that is available was done by people from operations research who have used evolutionary algorithms, but not evolutionary computation people. Okay, this is just on the same direction, that defining a good utility function is complicated, and in operations research, they take very seriously this whole business on how to build a preference structure for a problem, particularly if it's a real-world problem. And they distinguish very clearly a trade-off between spending more time working on a good utility function and spending more time searching through a very large set of solutions. That means they normally pay a lot of attention to this stage. What is worth doing? Should I spend a lot of time with a good utility function, which takes a lot of analysis and a lot of work, or I should just go to an a posteriori approach and deal with a larger set of solutions. I have some friends who have done real-world applications of multi-objective optimization with preferences, and in some cases, when the model they are using is well known, that they have worked with this model for a long time, they provide some weird utility functions. For example, an aggregating function with weights defined with 4 decimal positions. That sounds very strange. But the reason for these values is not random. These are very specific values related to the specific features of the problem, because these people know this problem very well. So what they have is already a very accurate model of the process that they want to optimize, and all they want is a slight improvement on the solutions that they already have. So in those cases, this part is very simple, but in an open problem, it may be very complicated. So okay. So let's talk now about the incorporation of preferences into a multi-objective evolutionary algorithm. So of course, the 3 approaches are possible. We can incorporate the preferences before the search, during the search, and after the search. If we go for before the search, then normally what people use is an aggregating function, because that's like the easiest way of doing this. Interactive approaches are not very common. There are few, but they are not very common. And of course, a posteriori is like every multi-objective evolutionary algorithm can be considered as an a posteriori technique, because we don't incorporate any preferences. So we have the three options. Now, regardless of the stage at which we incorporate preferences, the goals of doing this should be clear. The aim is to magnify or to concentrate this search on a certain portion of the Pareto front. For example, in here, all this is the Pareto front. But it turns out that the decision maker is only interested in this very small region. So you see, you incorporate the preferences since the earliest stages of the search, so that most of the search effort is concentrated in this small region. I'm not interested in generating solutions here or here, only here. So this helps a lot to the user. Okay, so we will review now some of the most representative work in this area. apparently these guys, Tanaka and Tanino in 92, were the first to incorporate preferences from the user into a multi-objective evolutionary algorithm. In this case, and this is a very interesting paper, not very well known, they use a genetic algorithm to generate non-dominant solutions and an interactive approach to incorporate preferences from the decision maker. So preferences are expressed in 3 different ways: by choosing satisfactory and unsatisfactory solutions. So that means the decision maker is presented with the solution, and he or she decides this is good or this is not good. The second choice is by defining aspiration levels, that is, goals in objective space. So solutions that are far from the goals are considered unsatisfactory. And the third is by defining the worst acceptable level for each objective. So any solution below this level is considered unsatisfactory. So in the 3 cases, is basically the system wants to know what is acceptable and what is unacceptable. So those are the 3 obvious ways of doing it, right? You directly ask. You ask the user to define goals or targets, or you tell the user what will be the worst that you will accept for this objective function value. Fonseca in 93, in his paper of MOGA, which I told you he was solving a real-world problem, the design of a gas turbine for Rolls-Royce. In that paper, he made a similar proposal as that of Tanaka and Tanino. In this case, he extended the ranking mechanism of MOGA to accommodate goal information as an additional criterion. He used the goal attainment method, which we saw the first day. It's a very relatively recent technique from the 70s. And the decision maker was allowed to supply goals at each generation of the multi-objective evolutionary algorithm. So again, this was interactive. And with these preferences, the user reduced the size of the set that he was inspecting. So this is very similar to the idea of Tanaka and Tanino, in which he starts with a whole set of non-dominant solutions, shows this to the user says, I prefer these sort of solutions from this set, and then the size of the set is being focalized only to the region of interest for the decision maker. In a further paper, this work was extended in 98, and in this case, they define a relational operator that incorporates the preference given by the decision maker. The ranking of MOGA is based on this operator, and the operator relies on the use of priorities defined by the decision maker. So if the decision maker doesn't express any preference, then all the objectives are assumed to have the same priority. That means no preference information. And this is much more flexible. This is the paper he published in the Transactions on Systems, Man, and Cybernetics in 98. And it's an interesting idea because in here the difference is there is no interaction with the user. The user expresses a priori his preferences. These preferences are used to modify non-dominated ranking, and the modification automatically produces the solutions the user prefers. So it's sort of automating the decision-making process. Hinchliffe in 98 used MOGA from Fonseca and Fleming to incorporate preferences from the decision maker into a multi-objective genetic programming system that was applied to the modeling of chemical process systems. This is also an interesting approach. It's not that novel in the sense that the multi-objective evolutionary algorithm is just a variation of MOGA. It's pretty much the same scheme. The main difference here is that they use genetic programming. Genetic programming, as I told you before, is an evolutionary algorithm that is considered a variant of the genetic algorithm in which instead of using binary strings, as we use in the genetic algorithm, we use trees. And these trees represent computer programs. So we are directly evolving computer programs. And it's very powerful, can be used for any sort of application. In the early days, it was used for prediction problems. For example, predicting the behavior of the stock market, that's forecasting. Today is used for many other tasks, like designing, for example, filters, designing circuits. In this case, is for modeling a plant, a chemical plant. These are normally complicated problems. The main limitation of genetic programming is that its computational cost is very high. So it can be unaffordable in many cases. Shaw and Fleming in '97, they experimented with different approaches, incorporating preferences into a multi-objective scheduling problem that they solved with MOGA, because Peter Fleming was the advisor of Carlos Fonseca, so they were using the same algorithm. In this case, the experiments showed that the use of preferences expressed a priori using an attainable or desirable goals was better than using a problem-specific heuristic. And in this case, they concluded that constraining the preferences has a great impact on the performance of the algorithm. This was actually a very interesting application, because they were solving a real-world application with Unilever. It's a British company that produces food, frozen food, and they needed to optimize some schedules they use for distributing the food. So they did that using a multi-objective evolutionary algorithm. But in this case, as I say, they provided ahead of time the goals that the customers expressed. Well, in this case, the customer was the company, that the company wanted. And they put these goals, and they found this to work better than doing this in an interactive way. Because interactively, sometimes the user cannot provide the information very, very well. And it was more flexible as well. Another approach based on definition of desired goals was proposed by Kei-Shen Tang in 2003. In this case, again, the decision maker defines goals that are used to modify the ranking of a multi-objective evolutionary algorithm. And they also allow the use of soft and hard constraints. I mentioned before, a soft constraint is a constraint in which you can violate it a little bit, and this is still acceptable for the user. And a hard constraint is one that by no means can be violated. It has to be satisfied. Otherwise, the solution is not acceptable. So in this case, they run separately individuals that satisfy the goals from those that do not satisfy the goals. And this is found to be more flexible than the scheme of Fonseca and Fleming, because it allows to use logical operators, for example, and, or. And also, it allows the specification of don't care priorities. The don't care will be like the incomparable, right? I don't really care between these two solutions, which one you choose. They do it a priori, although they suggest in the paper that this could be done interactively. Said and Youssef in '99, they propose a technique in which the decision maker defines a set of goals or acceptable values or limits for each objective function, and using those goals, we can modify the selection mechanism of a multi-objective evolutionary algorithm so that only solutions that are nearest to these goals are selected. In this case, something interesting is the definition of nearest is made using fuzzy logic. Fuzzy logic is used, as you probably already know, for defining solutions in which you are not totally certain of what you are choosing. You have some uncertainties involved in the decision-making process. Shibuya also proposed another scheme in which the decision maker has to provide preferences interactively during the evolutionary process and expresses preferences through pairwise comparisons of images. This is a computer-generated animation application. It's kind of an unusual application. And then the user, the algorithm sorts the solutions available based on these preferences that are expressed based on these pairwise comparisons by the decision maker. Carl Yamoidev also some years ago in '99 proposed a technique that transforms goal programming problems into multi-objective optimization problems that he solves using a multi-objective evolutionary algorithm. In this case, the decision maker has to assign targets or goals that wishes to achieve for each objective, and these values are incorporated into the problem as additional constraints. So this is kind of an unusual thing because goal programming is, as you know, a mathematical programming technique. It's not very usual to use an evolutionary algorithm to solve a particular part of a mathematical programming algorithm. But in here it's used to incorporate preferences, so it's kind of interesting. The objective function attempts to minimize absolute deviations from the target. So this is similar to Keishen-Tan's approach. At the end of the day, the user is providing goals, and the algorithm tries to minimize deviations with respect to those goals. He uses a utility function. Utility function is like a linear aggregating function with weights. Uses deviations from the goals using the min-max method, or directly priorities. This will be a lexicographic method. So all these can be used for deciding. Elio Barbosa, this is also a very unusual application. He proposed a coevolutionary genetic algorithm with two populations. One has solutions to a problem, and the other one has weights. As I mentioned before, in coevolution, the idea is that we define two populations, and these populations are related to each other. So I have population 1, and I have population 2. And the idea in coevolution is that the fitness of this population depends on population 2, and vice versa. The fitness of population 2 depends on population 1. So it's this sort of a scheme has been used a lot in evolutionary computation for solving large-scale single-objective optimization problems having more than 100 decision variables. Coevolution can be cooperative or can be non-cooperative. Normally, we have used cooperative coevolution. That means the two populations are friends, right? They have a good relationship. So they share information. In the non-cooperative scheme, there is no information shared between the two populations. So in this case, the problem he's solving is to ask the user, he is designing graphs randomly, and he wants to choose the most beautiful graphs. So he asks the user, what graphs do you prefer? So to try to model the notion of beauty that the user has. So it's kind of an unusual application. So the user ranks solutions based on subjective preferences because, you know, beauty is always subjective. And the ranking is used to determine fitness of the population of weights. This is interactive because the user is being presented solutions during the whole search process to do the ranking over and over again. Borges and Barbosa propose another approach similar to goal attainment. In this case, the decision maker is required to provide a constant vector that contains the limit values for each objective function. So this will be similar to Tanaka's approach. One of the three techniques was, you give me a minimum level of acceptance for each objective, and I will try not to go below that. So these limits represent maximum or minimum values that are acceptable by the decision maker, and then the original objective functions will be penalized based on the values that we obtain. Of course, if the values are beyond the bounds, beyond the maximum or the minimum, then we penalize. This is an a priori approach because this information is provided ahead of time. Kato, in 2005, proposed an interactive fuzzy satisficing method in which he uses fuzzy logic to define goals with a membership function. The membership function is what we use in fuzzy logic to express the probability of accepting a solution. And the membership function in this case is used to incorporate the preferences. he uses this concept called M-Pareto optimality, which was proposed by Sakawa in '93, in which an aggregating function is adopted to represent the degree of satisfaction or preference of the decision maker based on satisfying these fuzzy goals of the problem. In this case, there is one membership function for each objective function, and all the membership functions are aggregated into a single expression. They are mixed together, and then they use a minimax formulation so that the decision maker expresses aspiration levels using reference membership levels. So this is a hybrid between fuzzy logic and a utility function. June proposed the generalized data envelopment analysis, GDEA, in which again the user is asked to give aspiration levels for choosing desirable solutions from the Pareto optimal set. This guy is actually very famous in multi-objective optimization, Nakayama. This again is interactive because a nonlinear aggregating function is optimized by a genetic algorithm, but the decision maker has to define during the search aspiration levels for each objective, as well as the ideal values for them. These ideal are like the desirable targets for each of the objectives. Okay, utility functions. Fonseca also proposed in '93, in his paper of MOGA, the use of an expert system to try to automate the task of the decision maker. In this case, the idea was to use an expert system with knowledge expressed a priori by the human to automate the process. If you are not familiar with expert systems were designed long time ago. It's one of the oldest developments in artificial intelligence, and basically operate based on if, then, else rules. Some of the pioneers of artificial intelligence realized that in certain tasks, humans don't use a specific knowledge about the problem they are solving. What humans use is experience. This is very weird. So there are problems that we can solve without having a real knowledge of what we are doing. It's just like intuition. So I will give you an example. If a chef, a very good cook, when these guys publish a recipe for cooking something, they put the ingredients, they say the amounts you have to put, how to mix everything, all the instructions, right? That's what a recipe is. However, if the guy who wrote the recipe, or a good cook, a good chef, goes on and prepares this dish himself, and you observe the guy, you will see he doesn't follow exactly the recipe. They always modify something in the recipe. And if you ask them why, they will give you some weird explanation. The explanation is related to their own experience. They know, for example, that certain ingredients have to be, I don't know, heated a longer time or a shorter time than what the recipe says, because otherwise the flavor is going to be different, for example. But this they learn by experience, by doing this many times. They know that. So this is the knowledge that expert systems store. In the early days of artificial intelligence, expert systems were designed to try to automate these complex decision-making processes that we had, in which we relied on humans. But the problem was humans had to provide this knowledge to design the expert systems. And in most cases, they were reluctant to do it, because they felt that if they provided this knowledge, they will be without a job. So they didn't work as expected. But that was the idea of expert systems. So they are still around, of course. So the idea of Fonseca was, let's do an expert system that contains this preference information from the user, so that we don't have to ask the user. We only ask once, and that's it. This sounds easy. In practice, it's difficult because in many cases, the human expert will be reluctant to give this information. Tanaka also experimented with an interactive approach using a utility function. In this case, the decision maker expresses preferences, and then the system that he designed uses a normalized radial basis function network to bias the selection pressure of a genetic algorithm. This radial basis function network is a neural network. In the morning in breakfast, I was discussing with somebody about neural networks. They were asking me, neural networks are a different tool. They have nothing to do with evolutionary algorithms. In a neural network, we have some circles. These are called weights. And we have inputs to the network, and then this network has outputs. Perhaps from the 4 weights, we produce a single output. Perhaps we have 4 inputs, but only 1 output. Neural networks are meant to model the brain. It's of course a very raw model of the brain, and they are meant to be used for classification. Classification is a very common task in pattern recognition. You know, I have a set of objects, and I want to know how many of these objects belong to class 1, how many belong to class 2, and so on. So neural networks have been around for a long time. They were created in the early days of artificial intelligence, and they have been used combined with evolutionary algorithms. For example, these weights, how to define these weights, and there can be several layers of weights. What we call the topology of the neural network can be optimized with an evolutionary algorithm. Some years ago, some student of mine asked me, why is that I didn't work in that area of optimizing, for example, the topology of a neural network. And I told him that for me, this is a very strange research area because neural networks are a heuristic also, and evolutionary algorithms are a heuristic. So if you use a heuristic to optimize the behavior of another heuristic, it's like asking a blind guy to help another blind guy to cross the street. Right? It's not going to be of much help because none of them know what they're doing, right? So one, you don't know how to use it, but it's going to be optimizing the other heuristic that you also don't know how it's behaving. So I don't have much faith in that area. But it was a very hot area back in the 90s. Today it's not that popular anymore. They now use something called neuroevolution, which is a much more sophisticated technique. And today, you have probably heard of the term deep learning, that people are going crazy with this. Deep learning is just a neural network that has many layers. As you increase the number of layers, training the neural network, because they need to be trained, that means you put samples and obtain results, and based on these results, you tune the classifier. So if you use more layers, it's more expensive, computationally speaking, to do the training. It takes longer. However, the neural network behaves better. It has a better performance. So for many years, people were reluctant to use too many levels, too many layers to do the training because it was just unaffordable. But today, since we have access to clusters of computers, some people decided to go for that, to use these big clusters of computers to train these neural networks with many layers. And they use them for complex classification problems. So deep learning normally involves using supercomputing or grid computing because it's just very expensive. But the neural network itself is the same. There is nothing new in the neural network. It's just you are adding layers and layers for the training. But that's where the money is right now. Many people want to do deep learning. So in this case, he uses this neural network to bias the selection pressure of a genetic algorithm that is, will move towards the region that better approximate the preferences from the decision maker. Who, this is an interesting one, in 96 and Greenwood in 97, use elements of something called imprecisely specified multi-attribute valid theory. It's a variation of multi-attribute theory. To perform, this will be decision making in the presence of uncertainty. You are not completely sure about your preferences on the non-dominant solutions, so this is a method that can be used. So instead of ranking the attribute of the problems, we rank a set of solutions. And preferences are incorporated in the survival criteria of the multi-objective evolutionary algorithm to bias the search towards the region of main interest. So using as a basis the preferences expressed by the decision maker, the approach produces a set of equations that have to be solved. In the original version, it was a set of nonlinear equations that's difficult to solve, so they managed to modify the algorithm so that it will produce a set of linear equations that is easy to solve. So this is a compromise between using no preference and a utility function. It's also a priori because you have to do it before doing the search. Another interesting approach is this guided multi-objective evolutionary algorithm that also uses the concept of utility of function. It was proposed by Jürgen Branke when he finished his PhD in 2001. The idea here is to express the preferences of the decision maker in terms of maximal and minimal linear weighting functions that correspond directly to slopes of a linear utility function. In this case, the authors determine the optimal solution from a population using the previously mentioned weighting functions. So in this case, he uses a ranking of solutions, and the ranking of solutions expresses the preferences of the decision maker, but combines this ranking with the generation of two linear aggregating functions or weighting functions. So, and he tries to approach the border between what is desirable and non-desirable. It's kind of an interesting approach. It has some problems though. He uses the original NSGA for the search, and then in a further version replaces NSGA by NSGA2. It does have some problems. I won't get into details, but it has some disadvantages. Meneghetti, he used LUTA, local utility approach, in which the decision maker is asked to say which solution prefers out of a set of solutions, and no other information is required. This is wonderful, right? It's just, from this set, tell me which one you like, and that's it. Then the algorithm proceeds in two stages. In the first stage, it checks any possible inconsistencies in the preference, that is an intransitivity, and advises the decision maker to remove them. So if it detects an inconsistency, it will tell. In the second, it proposes a composite utility function, which is made up of the sum of the piecewise linear utility functions. All these linear utility functions were constructed based on each question that the decision maker was asked. Whenever he was asked, please tell me which one do you prefer, then a utility function will be built. And at the end, we have a global one. So the preferences are expressed in this case as inequalities between the utility functions and the solutions available. In other words, the inequalities define a feasible search space for the algorithm, so that defining the composite utility function can be modified such that the search is constrained to solutions that are only in the region that is of interest for the user. So it's an interesting approach. This is an a posteriori approach, but it could be actually be done interactively. Dragan Bekov. Okay, we move now to preference relations. This is another family of methods. Dragan Bekov, he was working with me in England when I was there back in '98, and then he moved to Canada, went to a company. In his PhD thesis, Dragan proposed the use of binary preference relations that could be expressed qualitatively. This is very, very nice. The user could use words like saying this solution is less important, is more important, or equally important to this other one. And then these words were translated to weights, to numerical values. And these numerical values were used to modify the search of a multi-objective evolutionary algorithm. So it was not that sophisticated, but he provided a different ranking scheme which worked reasonably well. This is similar to a method that we saw, that you certainly forgot about in the first lecture, the surrogate word trade-off method. But unlike that method, binary preference relations can find concave portions of the true Pareto front, which is an important distinction. It works even if the Pareto front is non-convex. This is Dragan. This is an a priori approach because the weights are assumed constant throughout the optimization process. However, nothing in the approach precludes its use in an interactive way, can be used interactively. There are some practical issues that Dragan details in his paper in the transactions. For example, in some cases, the user may be asked a very large number of questions. This could happen, but it's not really a major issue. In practice, normally, it's not that bad. This scheme was used in a real-world problem that these guys were working on at that time from British Aerospace. It was a problem that had 12 objective functions. And I think they were happy with the solution they found at the end. So the direct use of weights to estimate the importance of solutions that have been already identified as Pareto optimal has been suggested by several other people. For example, Peter Bentley in his PhD thesis in '97, he considered a property called importance, which provides additional information regarding the sort of solutions that the decision maker prefers. This is coupled to a genetic algorithm used in ranking, but not Pareto ranking. He uses a different kind of ranking. This is actually similar to one proposed by Bemuri and Cedeno in '95. And this approach, something very interesting is that in its time, it was totally disregarded. Nobody in evolution computation liked this approach. Over the years, some people used this for many objective optimization. At that time, nobody found any use to it. So once individuals are ranked, the importance that the decision maker assigns to each objective can be used as a weight, and the fitness now is a weighted sum of the average ranking. So it's kind of a neat idea. It works easily. It's not so intuitive for the user what you are doing. This is also a priori because the preferences have to be expressed before doing the search. Also, it's worth mentioning that this is one of the few attempts to develop a formal decision-making model for evolutionary multi-objective algorithms that was in Dragan's thesis. This is another interesting one. Rolf Dreschler, in 2001, he proposed the use of satisfiability classes to model preferences from the decision maker. He uses a relation called favor. Favor is not a partial order because it's not a transitive relation. It's similar to Pareto dominance, it's not equivalent to Pareto dominance. That is something important. So he divides the search space into several categories: superior, very good, good, satisfiable, and invalid. And solutions that are generated are analyzed in terms of their quality to see in which of these categories they will fit. So it's kind of an interesting idea. However, not many people follow up on this. This also, the relation favor, can be used for many objective optimization. At least some people tried some years ago. It was proposed in the context of a problem in which they were trying to design circuits, electrical circuits. So after sorting the satisfiability classes regarding their quality, we obtain a ranking of solutions. And then preference relations are modeled using a directed graph that is recomputed at each generation without any human intervention. One criticism to this approach is that incomparable solutions may be placed in different classes, even if the decision maker wants them to be in the same class. But this is a more subtle problem. I won't get into the details of this. Another proposal that is very interesting also is from Ivan Hughes. Ivan Hughes, he was in academia for several years, but then he created his own company in England. he made a proposal to modify the ranking procedure of an evolutionary algorithm using preference information provided by the user. In this case, he uses expressions that incorporate information about both constraint violation and priority satisfaction. This is very interesting because he handles both things at the same time, and also uncertainties and noise. And all these affects the dominance relation. So it's very, very interesting, it's very elegant. But again, there was no follow-up on this work. Okay, I think this is the, well, it's not the last, one of the last groups. Outranking. Outranking is a technique with which is the most representative in the French school. And there are several algorithms for doing outranking. Actually, Professor Figueira has worked a lot on outranking. This is an example, Requiec. In 2000, they proposed outranking, an outranking method called Prometi 2. This, we talk about this in the first lecture. This algorithm computes a net flow, and this for each individual, and this value from the net flow is used to rank the population. So it imposes a complete preordering of preferences. Then weights are assigned to the objectives. This the decision maker has to do. And the algorithm is used in an interactive way because the decision maker has to modify the weights during the search. Something interesting is they use something called branching on population, which is basically the creation of intermediate states based on the preferences expressed by the user. So this is an interesting work. This guy, Brahim Requiec, he got his PhD, I think, in Belgium. Guimaraes Pereira, she used Electre. Electre 1, all the Electre algorithms, there is Electre 1 up to 6, I think. All of these algorithms are also outranking methods. He coupled this with a genetic algorithm and used this to generate alternative routes between two geographical locations. So this is an interesting problem. This was actually her PhD thesis. So these routes are generated and then compared by pairs in each of the objectives under consideration. And then she has an index that describes the outranking relation. That means the preferences from the decision maker. And this index is calculated based on the comparisons, and then uses an interactive, an aggregating linear function. So it's not that novel, except for the fact that she uses outranking. In another paper, she used Prometi and couples Prometi to a multi-objective evolutionary algorithm. In this case, the non-dominated vectors are generated, and then again, pairwise comparisons are performed, and the alternatives are ranked in terms of the preferences expressed by the decision maker, and again, uses a linear aggregating function to decide the direction in which she will search. Then she computes differences between the intensity of preference, which is defined using fuzzy logic, for each objective and each pair of alternatives. This intensity of preference means how much I want this to happen. This will be, is it really important or not? And this she models using fuzzy logic. It's another interactive method. Massevouv, these are people from Canada. They use also Prometi 2 with a weird genetic algorithm. It's called the diploid genetic algorithm. You know, genetic algorithms normally are called haploid because genetic algorithms have a single chromosome. The chromosome is the binary string. If you have implemented some genetic algorithm, the genetic algorithm, the traditional one, has a binary string and in these binary strings, the segments represent variables. For example, this can be one variable, this can be another one, this can be. You normally concatenate all the decision variables using using binary numbers. But typically, the genetic algorithm has a single binary string. So this is called a haploid. However, there are some weird genetic algorithms in which we have two strings in the same chromosome. They don't have to be the same. You may have different binary values. So this one is called diploid. Of course, one issue here is how do you decode, because decoding means to convert this binary number into the actual value of the decision variable, x1. x1 is probably a real number, but I encoded this as a binary number. So there has to be a way of mapping. But if you have two strings, how do you do that? So there are some techniques for doing that, some operators for this. But diploids are not very, very common. In theory, you can have multiploids. But in nature, most species have diploids. We have diploids. So if you have seen this in science fiction movies, right, they have, back in the 80s, in my time when I used to go a lot to the movies, they had these weird stories of a guy who somehow mixed with a crocodile, and there was this crocodile man, right? It was the offspring. This, of course, is not possible because humans we have 23 pairs of chromosomes. It's pairs because we have diploids. We can only reproduce with another species that has exactly 23 pairs of chromosomes. And the only species on Earth that has 23 pairs of chromosomes, as far as I know, are humans. We can only reproduce with humans. We cannot reproduce with any other species. The same applies for all other species on Earth. They can only reproduce with their own species because of the number of chromosomes. But why do we have two? Why do we have diploids? This has been a mystery for many years. Some evolutionists believe that the reason is that the second string is like a backup. In case something goes terribly wrong with us, there is a backup to restart the species. I believe they don't really know. This is just a theory of why they have that. But these diploids are not very common. So in this case, the decision maker is asked to express preferences for each pairwise comparison of alternatives. So again, in all these methods, the non-dominant solutions are compared by pairs, and the decision maker assigns weights that express relative importance of the objectives, and then the information is used to compute this so-called global concordance index and a discordance index. These are used in electric. With these indexes, then the authors generate outranking degrees for every pair of alternatives. And this allows to rank alternatives so that a final recommendation can be made to the decision maker. Parreiras and Vasconcelos, these are people from Brazil, they also use Prometheus 2 combined with a multi-objective evolutionary algorithm. In this case, they use a Gaussian preference function and a normalized linear aggregating function for computing global preferences. And the search engine in this case was the NSGA2. Okay, I think this is the last one, the fuzzy logic. Fuzzy logic has also been used to incorporate users' preferences. Boguet, in the mid-90s, used a fuzzy controller. A fuzzy controller is an algorithm, it's an artificial device that people use a lot in the 90s to tune the parameters of genetic algorithms. Since tuning the parameters is a difficult task, one possibility is, of course, to use these fuzzy controllers, because fuzzy controllers are meant to tune anything, right? Any sort of controller that you have. And an evolutionary algorithm can be seen as a controller. So back in the 90s, several people tried to do this. However, there were different degrees of success in doing this, but evolutionary computation people didn't like much to use fuzzy controllers because evolutionary computation people normally doesn't know much about fuzzy logic. So they didn't understand in general how these things work. And if you don't understand how something works, you normally don't trust these things. So that's normally what happens. So in this case, the fuzzy controller is meant to regulate the selection pressure of a multi-objective evolutionary algorithm by using some goals pre-established by the decision maker that define the desirable behavior of the population. So in what direction is that I want to move? Then they use a set of fuzzy rules to modify the selection mechanism of the multi-objective evolutionary algorithm. And of course, you want to avoid deviating from this goal. In this case, this approach is actually used only to keep diversity, but it can be used also to incorporate preferences. Something interesting is the goals can be expressed in vague terms because fuzzy logic allows uncertainty. So this is also very nice. Other fuzzy controllers were proposed by other people. For example, this guy Esbensen at the University of California at Berkeley in the mid-90s. He used also these sort of controllers, but he used these for online and offline performance of the multi-objective evolutionary algorithm, which was used also to guide the search. So it's very interesting because in the mid-90s, we didn't really have performance indicators. The first performance indicators started to get used in the late 90s. But this guy who was in electrical engineering, he suggested to use a fuzzy controller as some form of online performance measure, as a performance indicator. So he said, what I would like is to maximize the diversity of the non-dominated vectors in the population, maximize the number of non-dominated vectors, maximize the bounding volume of the set of non-dominated vectors, and make the center of gravity of the final solution set close to the origin. So it's very interesting because if you see these goals, they are very similar to Sitzler's goals in his paper from 2000. But this was proposed a few years before Sitzler. And this notion of maximizing the bounding volume sounds pretty much like the hypervolume. It's an intuitive notion of hypervolume. By bounding volume, he means the volume covered by all the solutions in the approximation, trying to avoid that all the solutions are very close from each other. So it's very, very interesting. So in this case, he measures these four things and uses the fuzzy controller to make sure that his search engine is performing based on these four measures. Pirjanian, this is a robotics guy. He used fuzzy rules to generate weights that will narrow the search of a traditional multi-objective optimization technique. And then in 1999, he used these fuzzy rules for the multi-criteria decision making of the behavior, where he tried to optimize the behavior of a robot. So his approach operates in 4 stages. First, he finds feasible solutions based on physical and other constraints, then finds Pareto optimal solutions, finds satisfying actions from these solutions. Of course, these satisfying are according to the decision maker, whatever the decision maker thinks is acceptable. And then find the most preferred action using some other criteria. So in a paper from 1999, he uses a single robot that aims to reach a certain target, but later on he generalized this to several robots with the task of surrounding and capturing the target. They use weighted sums to generate the Pareto front and use lexicographic ordering, goal programming, and interval criterion for finding satisfying actions. All these approaches were a posteriori. Yao Shujin also did some interesting work back in the year 2002. He proposed an approach for converting fuzzy preference relations into interval-based weights, which are combined with his method from 2001, this weird linear aggregating function. This is similar to the approach of Dragan, but instead of converting the fuzzy preferences into a single weight, he converts this into an interval. Rather than a single value, it's an interval of values. Goes from one value to another value. So he uses preferences matrices and real value preference relation matrices. So it's a very interesting approach. It has, of course, some limitations because it won't be able to work with non-convex Pareto fronts because the scheme to control the preferences won't allow to generate solutions in the non-convex parts. This is an important restriction with respect, for example, to Dragan-Bekovic's approach. This one is able to generate solutions in the non-convex portions of the Pareto front. Wang, in 2005, they proposed an approach based on the use of a fuzzy set-based aggregating function to express preferences from the user. And in this case, they rely on two things. First, a set of weights that express the importance of the design attributes and a degree of compensation among these design attributes. So if we change the weights and the compensation factors, we can generate different portions of the Pareto front. This is also interactive. They actually use this agent-based system to ask preferences from the user during the search. And the preferences are refined based on the constraints on the problem and on a fuzzy preference aggregating function. So it's kind of an interesting application. Farina, he analyzed the limitations and drawbacks of Pareto optimality when dealing with problems having more than 3 objectives. I mentioned yesterday that the area of many objective optimization was really originated with the work of Marco Farina. Marco Farina, in the year 2002, had already identified the main limitations of Pareto optimality in high dimensionality problems. So he says Pareto optimality is unsatisfactory for 3 main reasons. First, it does not consider the number of improved or equal objective function values. Second, it does not consider normalized size of the improvements. And third, it does not consider preference among objectives. So based on this analysis, he proposes 3 alternative definitions of optimality. These are actually relaxed forms of Pareto optimality. K optimality, KF optimality that uses fuzzy numbers, and fuzzy optimality. These definitions are able to address the limitations of the original Pareto optimality when solving problems having more than 3 objectives. This is meant for many objective optimization. In this case, fuzzy logic is not really used for the preferences of the user, but for modeling the size of the improvements achieved in each objective. That is an interesting application. So objectives are given the same importance as when using Pareto optimality, but with this model, with fuzzy logic, he uses this information given by the membership function to extract subsets of solutions from the Pareto optimal set. But the purpose is not really for preferences, it's really for solving many objective problems. So it's a different aim. Carl Yamoidev also proposed a variation of compromise programming to bias fitness sharing in the original NSGA. This was done a long time ago, back in 99, and then an extended version of this was published in 2001. He uses a normalized Euclidean distance between objective vectors, but introduces unequal weights such that different importance can be assigned to each objective. So this biases the niche formation procedure of a multi-objective evolutionary algorithm, but does not produce a single final solution. It produces several. More recently, in 2005, Branke and Deb proposed a bias crowding measure. If he biased fitness sharing, it makes sense try to bias crowding as well. And they do this with NSGA too. So in this case, the user provides preferences as a direction vector, which is a central linearly weighted utility function. And then the crowding measure is biased based on this direction vector, so that only a fraction of the Pareto front is generated, not the whole Pareto front. So this is scalable to any number of objectives, or so they claim, and can also generate non-convex portions of the Pareto front. So it's an interesting proposal, but nobody really paid attention to this proposal. Sakawa also suggested an approach based on compromise programming. In this case, again, fuzzy logic is adopted. A minimum operator is defined so that it can integrate all the preferences into a single membership function. And then he uses compromise programming, this we saw in the first lecture, to guide the search of a multi-objective evolutionary algorithm. So this was applied to multidimensional versions of the knapsack program. Okay, if you want to know more about this topic, there are several references. This is a very old survey I published in the year 2000. Jose Figueira, he has a book with Matias Ergot and Salvatore Greco that was published in 2010. This is a massive book, it's huge, and it's an excellent reference on multiple criteria decision analysis. And also there are some more recent papers. For example, this is an interesting one with Tobias Wagner and Heike Trotman, is how do we incorporate preferences in an algorithm that is based, a multi-objective evolutionary algorithm that is based on the hypervolume. Can we use the hypervolume to incorporate preference? The answer is yes, it can be done. And this is a way. Using these desirability functions is possible to do it. There are many others. For example, how do we incorporate preferences if we use R2? The R2 indicators is also possible. Some comparative studies, in this case they compare progressive preference articulation. Progressive means interactive, is another word for interactive. And this is a more recent survey by Slim Bechik. This guy, I think he's from Tunisia, he published more recently a survey on preference incorporation. This is, I believe, the most recent survey that has been published on this topic. Other papers, preferences for many objective optimization, another survey on preference incorporation in multi-objective evolutionary algorithms. This is actually very similar to the survey I wrote, but this is from 2006. How to incorporate preferences in MOIA-D. This is a proposal from 2015. These are people from the Czech Republic. We also did some preferences some years ago with Antonio, who was my PhD student. So we have a paper on this, on preference relations at Gecko 2009, and then we published a journal paper on this in 2013, I believe. This is another interesting approach. Murat Koksalan is a very famous guy, a very big name in multi-criteria decision making. He's from Turkey. And he's very well known in this area. So he did some work on defining a technique for incorporating preferences into a multi-objective evolutionary algorithm. It was published in a special issue of the Transactions in the year 2010. Another one from Heike Trautmann in 2009, in which they incorporate preferences in noisy environments. This is tricky to do. Another method for incorporating preferences was published in the Transactions in 2012. A framework for studying incorporation of preferences, another method for incorporating preferences, the PI method. And this is an interesting one. This is more on the operations research side, but you can see Jürgen Branke, who is an evolutionary computation guy, is involved in this. They use something called the Choquette integral to model preferences in an interactive evolutionary multi-objective optimization algorithm. And this was published in the European Journal of Operational Research. So there are quite a few papers on this. So I don't know if you have a question up to this point. I know this is kind of a very difficult to digest topic if you have never done any work on incorporation of preference. Perhaps it was worse with Jose. Just aiming for it. You had a worse time. Yeah. The what? That's the method. K optimality is a relaxed form of Pareto optimality. That's Farina's technique. In K optimality, what he says is that if you have many objectives, for example, you have 6 objectives. In Pareto optimality, if you remember the definition, you have to be less equal in every objective and strictly less in at least one. So the problem with that definition is as you increase the number of objectives, it's more likely that solutions will be non-dominated between each other. Because the more objectives you have, the more unlikely it is that you will be better in some of them. So what he does with K optimality is to measure degrees of improvement. You say, okay, these values that I have for one objective, for example, I have 5 here for one algorithm, and the other solution has 4. I want to measure how much better this is with respect to the other. Not only counting, right? Not only saying it's less equal. No. I wanna know how far better. And K optimality tries to measure. So it defines preference or optimality in terms of the differences, and not only counting how many. If you are less equal in every objective and strictly less in one. This is a way of relaxing Pareto optimality. In the extreme case, K optimality becomes Pareto optimality. That's why it's called a relaxed form. Obviously, in many objectives, K optimality will produce more solutions than Pareto optimality. Will break ties. It's useful. Any other question? So this is important if you solve a real-world problem. In a real-world problem, as I said, normally the user is not interested in all the solutions, only some of the solutions. So you have to come up with a way of selecting those solutions or allowing the user to select those. That's really the use of this. In other cases, if you are solving some benchmark problems, some toy problems, this is probably not that useful. But it's a topic I had to cover because it was included in the outline. Right? Now, if you wonder if there is any code available for this, I believe there is no code available. That's my belief. I may be wrong, but I haven't found any source code available on incorporation of preferences. There are algorithms, but not. It's like if you have a problem, you found the code of the algorithm, but how to put your problem into the code, that's another story. That you have to figure it out yourselves. Right? You have to dissect the algorithm so that you can find where to put it. You can do it trial and error, right? You put it here, it doesn't work, then you move it somewhere else until you find. No, you need to find, I told you, the definition of the objectives. Once you find the definition of the objectives, normally there you will find the definition of the decision variables, and that's the only part you have to modify. It's just that when you release code in the public domain for other people to use, the underlying assumption is that the other guy knows how to use an algorithm, right? Any algorithm. You don't want to do the implementation because perhaps based on the paper, the implementation won't be accurate. That's one thing. But these guys who release the code, most of the time, they are not going to take the time to write a user's manual. Some people do, but most people don't do it because they don't have the time. You know, as an advisor, as a thesis advisor, you can ask the student to write anything you want for as long as they are students. Once they graduate, we have no control on them, right? It's a promise. They will say, yeah, I will do it. Yeah, I have promises from 20 years ago that are still to be fulfilled. So that is not going to happen. Once they graduate, they don't give a damn about the code. They will go away and forget about this thing. So there isn't much we can do. Some people, there are people who are very disciplined and they release the code and either have many comments in the code itself or they write a small user's manual so that people can figure out how to use the code. But there is some minimum knowledge you need to have, of course, about the code.
So this is normally not very difficult unless you don't know any programming at all, or you have no idea of how an evolutionary algorithm works. In that case, it will be more difficult. You will have to start by learning that first, and then you go to the code. My advice is read the paper first, and then download the code. Don't do it the other way around.
So what I'm wondering is that in decision-making problems, nobody has used the definitions of proper efficiency. There are lots of proper efficient points with geometry proper efficiency, mechanic proper efficiency, current effect
Well,
proper
that's
efficiency.
I'm not sure if they have. Probably they have. This is not a comprehensive review, so probably some people have. But in the papers I revised, I didn't find the use of proper efficiency. It's more common in operations research in evolutionary algorithms. And as I said, one problem is that most evolutionary computation people don't use these methods because they are not aware of it. Computer scientists normally don't have a background in operations research or class math, so all this is new to us. And in many cases, we don't want to mess with this because when you develop something related to incorporation of preferences, send it to a journal in operations research, those guys who are specialized in it, they will eat you alive. They will say, this is garbage, what you're doing makes no sense. So that discourages a lot evolutionary computation people to go in that direction. We only do it if we go with an operations research can guide us. And otherwise, it's a risky terrain. We're only missing one topic in this lecture, and then I will be. So if there are no more questions, we will go for the break. Come back at 11:30 to finish.